So, good afternoon, guys. Very nice to see you here. And today, I'm going to introduce some studies on the application of computational models to explore the characteristic of cardiovascular hemodynamics and assist in the development of medical device. I'm F.Liang from Shanghai Delta University and Sichuan University, as Lika has just introduced. So, I think when you put your finger at your wrist, you will detect some kind of movement, right? This is actually caused by the pulsation of blood pressure in our artery, which is usually called as blood pressure wave. Actually, blood pressure wave exists in all over our cardiovascular system, but it changes in its magnitude and the shape along our arterial system, right? Which is dominated mainly by the propagation and the reflection of pulse waves, actually. Pulse wave propagation and the reflection are again determined by some cardiovascular properties, like the dimension of the artery or the stiffness of the artery. So it is believed that arterial pressure waves carry very important information reflective of the state of the cardiovascular system. So understanding the formation and the change in arterial pressure wave can help us to understand the relationship between cardiovascular physiology and pathology, as well as for developing some diagnostic methods for cardiovascular function. So for this purpose, actually, computational models have been developed since 50 years ago. During these years, a lot of different kinds of models have been developed. So in this lecture, I would like to introduce two topics. The first one is we use computational models to address the changes in arterial hemodynamics during aging. And in the second topic, I will introduce the simulation of oscillometric waves in an upper arm curve and its application to explore new methods for estimating aortic pressure. So here we come to the first topic. We represent the arterial tree, as I show here, can see here. The arterial tree consisting of about 55 large arteries with a one-dimensional model, which has been proved to be able to well suited for the description of pathway propagation phenomena. But only this one model is not good enough because our cardiovascular system have other components like microvessels, veins, the pulmonary circulation, and the heart. So we couple this 1D model with a 0D model of the other portions of the cardiovascular system to form a closed loop model of the whole cardiovascular system. Later, we have also extended this model to include a more detailed description of, for example, the coronary circulation or the cerebral circulation. So in this way, we obtained a closed loop model capable of describing both arterial wave propagation and systemic hemodynamics. Here we show the governing equations. The 1D model and the 0D model are governed by different equation systems, and they are coupled numerically at the interface between the two models. So I'm not going into the details of the governing equations and the numerical schemes. Using the model, we first simulate pressure and flow waves in the cardiovascular system for a healthy young adult under resting conditions. Here I show the model simulate variation in pressure wave along the aorta from the root of the aorta, which is close to the heart, to the peripheral artery. You can see that the systolic pressure, which is the peak pressure of the pressure wave actually, increase along the aorta. This phenomenon actually is physiologically beneficial because the relatively low systolic pressure at the aortic inlet will reduce the stress of the myocardium. As for the blood pressure wave, you can say as for the blood flow wave, you can say the blood flow just decrease along the aorta because the distribution of blood through some branch arteries. And also because our model is a closed loop one, our model can also simulate blood pressure or flow waves in other portions of the cardiovascular system. Here, I just show some examples. For example, we can find that the largest pulse of pressure appear in the left ventricle, right? And the blood pressure becomes almost constant at the capillary level, and the pressure in the veins are very low with very weak position. And further, we use this model to simulate to study the effect of aging. Here we show the similar result for 3 ages, the 25 ages to 85 ages. This is advanced age, right? So what you can see from this figure that the augmentation of systolic pressure along the aorta disappeared at advanced age, right? This is not physiologically beneficial because the pulse pressure is increased and the systolic pressure is higher, which will increase the stress of myocardium. And the in vivo study also show similar phenomena. And then, why we use models? Because models can provide more detailed insight into the mechanism underlying the changes in arterial pressure, right? As for aging, there are 2 major changes in aorta. The one is stiffening of the aorta. The second one is aortic dilation. Here we separate the pressure waves simulated for young subject and old subject into 2 parts. The first part, the forward traveling part, and the second part is the backward traveling part. The backward traveling component is also called reflected wave. You can see from this figure that this dark one represents the reflected wave. You can see at a high age, the peak of the reflected wave increase, and the timing, the timing of the reflective arriving at the aorta is advanced. You can see it appear earlier. So this reflective wave will superimpose onto the forward traveling wave to form a pressure wave which has higher systolic pressure and a wider pulse wave. And usually it is considered that aortic dilation is kind of physiologically degenerative. But as from our numerical study, for example, if we for the aged subject, if we don't increase the dimension of the aorta, which means that without aortic dilatation, you can see that the pulse pressure and the systolic pressure both increase very significantly, which means that aortic dilation is not always bad. It can help to reduce the systolic pressure and the pulse pressure. So using the model, we further study how the changes in arterial pressure wave affects the energetics of the left ventricle. This figure shows the pressure volume loop of the left ventricle. From this figure, you can see that in order to preserve a constant cardiac output, an aged subject requires higher ventricular contractility, which will result in higher consumption of energy. You can see from stroke work from this figure, you can see that for the aged subjects, the stroke work is higher than the young subject, right? And then we move to the next subject of the next topic. I guess all you have the experience of measuring blood pressure, right? Usually, when you use a blood pressure device, you will measure your blood pressure at the upper arm here, right? The blood pressure measured here actually represents the blood pressure in peripheral artery. However, according to clinical studies, the central aortic blood pressure here, just near the heart, the outlet of the heart, are more accurate measure of cardiac load and are better predictor of cardiovascular events, which means that central aortic blood pressure is more useful than peripheral blood pressure. Unfortunately, we cannot measure central aortic pressure easily. The golden standard for measuring central aortic pressure is to use a catheter with pressure sensor. But this kind of measurement is invasive and cannot be applied to general clinical settings. So some researchers have tried to develop methods for non-invasively estimate aortic pressures. The basic idea is to derive central pressure from peripheral pressure by applying a transfer function. You can measure the peripheral pressure waves non-invasively at different locations. For example, you can measure the pressure wave at the fingertips, at the wrist, or at the upper arm. But this kind of approaches usually are not very applicable because they have some inherent limitations. First, they usually require complicated operations, and also they sometimes subject to uncertain errors in personalized measurement. So these 2 points are major problems with current method. So we propose a new approach. We propose to reconstruct aortic pressure wave from oscillometric signals of a suprasystolic branch curve. What is suprasystolic? Which means that the operating pressure of the curve is much higher than the blood pressure inside the branch artery, which will occlude blood flow through the branch artery. We have performed some theoretical studies to demonstrate some physical phenomena underlying the method. For example, we found that the oscillometric wave of a suprasystolic branch curve resembles the blood pressure wave in the branch artery. And the second one is the undercuff branch artery is occluded by the suprasystolic branch curve. And third is wave traveling time from the aorta to the proximal edge of the curve relates closely with the characteristic of the cuff wave. To show it more clearly, here I provide a figure here. You can see when the operating pressure of the curve is much higher than intra-artery blood pressure, the artery will be occluded and the blood flow through the artery will be blocked. and it will form a path between the aorta and the proximal edge of the cuff. This is the path here, right? And under this condition, we can still detect signals from the cuff. And this signal, if we amplify one signal, one wave from the cuff, we can obtain this wave. You can, on this pressure wave, we have two peaks during systole, the first peak and second peak. And from the time difference between the first and second peak, we can estimate the wave transmit time from the aorta to the proximal edge of the cuff using this equation. You can see we can obtain delta T from the pressure wave, and then we can calculate dt, which represents the wave transmit time from here to here, right? And based on these findings, we have developed a procedure for reconstructing aortic pressure wave from the cuff waves. Here we just show the show some figures. For example, you firstly obtained a cuff wave, and then we scale up the cuff wave to obtain a pressure wave very similar to the blood pressure wave inside the artery, and then we separate the pressure wave into two parts, namely the forward traveling part and the backward travel time. And then according to the wave transmit time from here to here, we can change the phase of the two waves and then reconstruct the aortic pressure wave here. So this kind of method have some potential advantages. For example, it is completely non-invasive and automatable, and it has improved accuracy in personalized measurement. So in order to verify the validity of our approach, in next step, we developed a computational model that integrates the cardiovascular hemodynamics, cuff mechanics, and arm tissue mechanics together. I'm not going to the details of the modeling methods. Using this method, we firstly simulate the inflation process of a branchial cuff, which is a process represent, for example, the measurement of blood pressure. If you have the experience of measuring blood pressure, you will see that the cuff pressure will increase rapidly firstly, and then decrease slowly, right? From our model, you can see that when the cuff pressure is much higher than the blood pressure, the pressure distal to the cuff decreased significantly, and the position of pressure disappeared. Following the decrease of cuff pressure, the position of blood pressure will recover gradually. But you know, when we measure blood pressure using this kind of curve, we are not using the information obtained from the curve directly. We are using the high frequency component of the curve information. So in order to obtain the high frequency component, we apply a high pass filter to the cuff pressure, and then we can obtain the cuff oscillometric waves. The cuff oscillometric waves are so-called high frequency component. Here we show the changes in cuff oscillometric wave with the cuff pressure. This is our model simulated result, and this one is the measured one. You can see they are quite similar. And further, we applied our model to simulate the suprasystolic curve. You can see here that we held the cuff pressure constant at a suprasystolic level. You can see the cuff pressure is much higher. It's much higher and it's constant. And again, we apply high-pass filter to this cuff pressure data, and then we can obtain the cuff wave. And as I mentioned previously, we have two peaks, and then we got that TP. Then from that TP, we can estimate the wave traveling time between the aorta and the proximal edge of the curve. And also we measured the suprasystolic curve wave. The upper panel shows the measured curve waves for young subjects and middle-aged subjects. And the lower panels shows the model simulated results. From these figures, you can see that there are some very specific changes in curve waves during aging. For example, when from young subject to old subject, you can see the second peak increase relative to the first peak, right? And further, we use our model to try to simulate a large population, because collect data from a large population is usually time-consuming and expensive. And also for quantitative analysis, it is usually difficult because every subject have his specific cardiovascular condition. So here we use our model to simulate some virtual subjects. Here in our model, we change some model parameter to represent the inter-subject differences. This model parameter characterize 5 major cardiovascular properties like aortic stiffness, branchial artery stiffness, cardiac contractility, total vascular resistance, cardiac duration. Also, we take into account the height. You know, everybody has his height. There are large variation in height among subjects. So then for each of these parameters, we set a certain range for it. In this way, we can simulate about 4,000 virtual subjects based on the variation of these parameters.
Sorry for you, can I interrupt you? And I just have an announcement about this classroom attendance. Пожалуйста, отметьтесь в чате сейчас. Sorry. Yeah, you can continue. You can continue. Okay.
Oh, no problem. Sorry, I go back here. Just wait a minute. Okay. So based on the virtual subject simulated by very model parameters, we perform numerical simulations to compare the estimated aortic pressure with our approach with the model simulate real pressure in the aorta. Here we show the results for the 4,096 virtual subjects. You can see that the model simulated the estimated aortic pressure correlates very strongly with the real aortic systolic pressure. You can see the R value is close to 1, but when we look at the errors, you can see the errors is about 4 plus minus 1.9. The mean value of the error is not so good. We want it to be close to 0, right? So next, because you can see here, we estimate the wave transmit time from that TP between the first peak and the second peak. But this one, this third peak TP, sometimes not determined completely by the wave transmit time, because our cardiovascular system is very complicated. Many factors may affect the appearance of the two peaks, right? So we try to make use of the characteristic of the cup wave. You can see for every subject we can obtain the cup wave. This cup wave will have some specific features. So we actually identify some feature points from the cup pressure wave. We use these feature points to try to correct the delta T. So after correction of delta T, we estimate the aortic pressure again. Now consider the correlation between the estimated and the real aortic systolic pressure is still very strong, right? Close to 1. But now the estimated errors have been reduced to about 0. I mean, the mean value is close to 0, which is good actually. So when we compare our errors with the errors of other existing devices, you can see our error is here, and some other existing device on the market is, for example, ARC solver is their error is in this range. These are ours. Please note that not only the mean value of our errors is lower than 3, but also the SD, the standard deviation, is much smaller than the existing device. So we can conclude that our method is superior to existing devices, and our approach, I mean, the accuracy of aortic pressure estimation is less influenced by cardiovascular conditions because we have a smaller SD. So it means that our approach may have better performance in personalized measurement, right? And based on our findings, we have applied for patent protection, and now we have got approved. And then we perform some in vivo clinical studies. Because limited by the the clinical resources, we just perform very preliminary clinical study, including about 40 patients. We got very good results. When we compare our estimated aortic systolic pressure with the invisibly measured systolic pressure, we can see that the R is still very high, close to 1. Now, we want to transfer our technology into real product. So now we have developed a prototype, and we perform some comparisons with existing devices. Sphygmomanocal XL is now one of the best devices for measuring central aortic pressure on the market. So our lab have got this device. We developed our prototype. We try to compare our measurement with the measurement with sphygmocal XL. So recently we performed tests on 43 subjects, with each subject being measured respectively with our prototype and the sphygmocal for 3 times. These are some results. You can see the correlation between our result and the sphygmocal, those obtained by sphygmocal, are high, with the error about 0 plus minus 2.9. So in this stage, our approach sounds good. Next step, we are try to, for example, we are trying to increase the sample size of our test, and probably in next year. We are working with a company to try to develop a device that can be put on the market. Hopefully, we will complete this work next year. So these are what I would like to share with you guys. So I would like to stop here. Thank you very much.
Thank you very much for you. Hello.
Hello.
I have a question.
Yes, please.
Could you please explain why the central pressure is so important?
Yes. Yeah. Here I just mentioned. Can see this. Actually, there are some clinical trials. They compare the predictive values of peripheral pressure and the central pressure regarding, for example, predicting the cardiovascular events. They found that the central aortic pressure is a better predictor of cardiovascular events. There are many this kind of studies, actually, large population-based studies.
But practically in clinics, how the central pressure is used to predict cardiovascular events? I mean, what events they can predict? Infarct?
Yes, yeah. In clinics, usually they don't care about central artery blood pressure, but in sense of preventive medicine, for example, for the measurement of patients with hypertension, you will take medicine to try to lower your blood pressure, right? But sometimes, you know, your peripheral blood pressure and central pressure just don't decrease in the same degree. Sometimes you can see that your peripheral blood pressure have decreased very well, but your central pressure will remain higher. This one application. This can help you to monitor the effect of your treatment for hypertension.
I see. Because the target is to reduce central pressure, not peripheral pressure. I see.
Yes, we try to reduce. Yeah, using central artery pressure, we can have a better predictor of cardiac events or the managing hypertension with patient with hypertension. That's why now we are working with companies to try to put it on the market with a major aim of applying this device to patients with hypertension, actually.
Okay. I shall ask students, do they want to ask you, Professor F.Liang, do you have questions, students? Okay, no questions. Thank you very much for your wonderful lecture and success story.
Thank you, Yuri. Thank you all.
Yeah, yes. Goodbye.
Bye.
Thank you very much for the lecture.
Thank you. Bye.
Thank you. Bye.